Hello, welcome to next session. In this session, we'll solve some questions of fluid mechanics and machinery. The topic is boundary layer flow. Question number 1 to 8 carries a common statement. The velocity distribution in boundary layer given by u by u infinity is equal to y by delta, where u is the velocity at a distance y from the plate, and u is equal to u infinity at y is equal to delta, and where delta is boundary layer thickness. So displacement thickness is given by, these are the options. Next question, momentum thickness is given by, these are the options. Energy thickness is given by, these are the options. Shear stress at the wall is, these are the options. And boundary layer thickness in terms of Reynolds number, these are the options. Shear stress in terms of Reynolds number, these are the options. Drag force FD is given by, these are the options. And drag coefficient is given by, these are the options. Okay. So now it is given that the velocity profile is u by u infinity is equal to y by delta, and we know that displacement thickness is delta star is equal to 1 minus u by u infinity dy integral limits 0 to delta. Now we can put u by u infinity is equal to y by delta, so it will be 1 minus y by delta dy, or now integrating it will be y minus y square by 2 delta, and limits at delta to 0, so delta minus delta square by 2 delta is equal to delta by 2. Okay, so that is the displacement thickness. And so answer for the first question is option B, that is delta by 2. Displacement thickness is delta by 2. Next is momentum thickness. So for momentum thickness we have that theta is equal to theta is momentum thickness, and integration limit of 0 to delta, and that is u by sorry, it is given by u by u infinity bracket 1 minus u by u infinity dy, and u by u infinity is y by delta. So putting this u by u infinity as y by delta, and then solving the integration, so it will be y square by 2 delta minus y cube by 3 delta square, and now putting limits, it will be delta square by 2 delta minus delta cube by 3 delta square. So solving it will be, momentum thickness will be delta by 6. So answer to question number 2 is D. Next is energy thickness. Energy thickness is given by delta double star, and it is given by u by u infinity bracket 1 minus u square by u infinity square bracket close dy integral limit 0 to delta. Again putting the value of u by u infinity as y by delta, so this will be y by delta minus 1 by y square by delta square bracket close dy, and solving it for integration. Okay, by integration, so it will be y square to delta and y 4 by 4 delta cube, and now putting the limit, that will delta to 0, so it will be your delta by 4. So solving it will be delta by 4. So answer to question number 3 is option C. Next, shear stress at the wall. Okay, shear stress at the wall is means wall means y is equal to 0. Okay, so from the Newtonian law we have tau naught is equal to mu d by dy is equal to y by 0, so y is equal to 0. That is the shear stress on the wall, and the velocity profile is given by u by u infinity is equal to y by y delta. Okay, and d by dy is equal to u infinity by delta. Okay, so this is the velocity variation. Okay, and d by dy is equal to y is equal to 0, and is equal to u infinity by delta. So putting this value here, tau naught will be equal to mu by mu u infinity by delta. So answer is option, question number 4, the answer is option B, mu u infinity by delta. Next is boundary layer thickness in terms of Reynolds number. So boundary layer thickness, to find out boundary layer thickness in terms of Reynolds number, we use von Karman momentum interval equation, that is tau naught is equal to tau naught divided by rho u infinity square is equal to curly theta by curly x, where theta is momentum thickness and tau naught is shear stress on wall. Theta we have calculated as delta by 6 in question number 3 in this case, and tau naught we have calculated here as mu u infinity by delta. So putting these values, so now it is curly theta by curly x, so differentiating it with respect to x, so curly theta by curly x, and it will be 1 by 6 into delta curly delta by delta x using chain rule. Okay, so here we So here we can take this delta x here and curly x here and b delta curly delta here, and then integrate. So it will be mu x by rho u infinity is equal to delta square by 12 plus 3. Now at the edge of the boundary layer or at the leading edge, there is no boundary layer thickness. So it means that x is equal to 0, delta is equal to 0. Okay, so c is equal to 0. Okay, so so this constant is 0. Now mu x by rho u infinity is equal to delta square by 12, or delta is equal to 3.46 mu x rho u infinity. So we can write it also like this: 3.46 root mu rho u infinity x root here, and it is multiplied by x. So it will be your boundary layer thickness in terms of the total number will be 3.46 x divided by root rex. Okay, so answer to question number 5 is B. Okay, next is shear stress in terms of the Reynolds number. So now to find out the shear stress in terms of the Reynolds number, we have tau naught that we have derived mu u infinity by delta, and putting the delta we have calculated here. Okay, so putting the value of delta here, so we can get shear stress at wall in terms of Reynolds number, that is 0.289 mu u infinity by x into rex. So answer to question number 6 is B. Okay. Next is drag force. So drag force is nothing but F the integration of shear force from length 0 to L, considering a small element in between 0 to L of thickness dx. At this element, the shear stress acting is tau naught and width of the plate is B. Okay, so the drag force is this tau naught into B into dx. Okay, and now tau naught we have in terms of x, this value. Okay, and we can put this value here. Okay, and integrate it to up to 0 to L to find out total drag force. Okay, so it will be 0.289 mu u infinity by x into rex b into x, or converting this rex into in terms of x also. So taking the term x of x. Okay, so it will be rho mu u infinity by mu u infinity root rho u infinity by mu root and 1 by root x into b into dx. Okay, so now we can take this mu out, u infinity out, this out, and b out, or it will be so it will be x raised to power minus 2. Okay, it will be x raised to power minus 1 by 2. Okay, now its integration will be x raised to power 1 by 2 by 1 by 2. Okay, now limits are 0 to L, so putting the limits, so we get this drag force as 0.578 mu u infinity root rho u L, okay, by mu. Okay, then drag coefficient is CD is equal to FD by half rho u infinity square. Okay, so FD is this quantity, and half rho u infinity square is this quantity. So A is your L into B. Okay, so CD will be your 1.154 B mu u infinity by rho L B u infinity square root rho u infinity L by mu, or it will be 1.154 root R L. So answer is option B. 1.154 by root R L.